Okay, hello everyone. My name's Katarina.
I'm Ellie.
And I'm Anna.
And today we're going to be talking to you about supercapacitors and the role that nanomaterials play in them, which again we just learned this morning. So in today's role, conserving energy and finding effective forms to preserve energy is really important and crucial in order to resolve our environmental problems. And so one way to do this that is currently still under research is if we can develop ways to find batteries that can store enough energy and charge faster. So if you could imagine your phones or your electric vehicles charging in a matter of seconds or even minutes and still using that energy that you put into your car or phone and use it for very long periods of time, that's exactly what supercapacitors can help us be able to do. And so there are two ways that we store energy, and that's through batteries and capacitors. And so what we learned this morning was how batteries have a high energy density, but a low power density. So if you can imagine, an analogy for this would be like a young child who has a lot of energy, but they don't have a lot of power. That would be an analogy for how batteries and their energy densities work. But a capacitor has a high power density and a low energy density, kind of how a power lifter lifts very heavy dumbbells, and they only usually do it once, but they use all of their energy and all of their power in that one use. But supercapacitors have a perfect balance, and they are a perfect bridge of what batteries do and what capacitors do. So they have a high power density and a high energy density. So what makes supercapacitors very effective is the use of nanomaterials. So what we did this morning when we made our own supercapacitors was we used a nanoporous material, which was carbon. And why they're so effective is nanoporous materials and nanomaterials in general have a very high surface area, which means that because of the high surface area, they have the ability to withhold lots of energy, which is why they're a very good use for batteries and withholding all of this energy. So this combination of fast charging and longer lasting batteries results in lots of energy saved and could definitely resolve some environmental problems.
Okay, so I'll be explaining the analogy. So we have 3 runners here, all in an 800-meter race. And so all of the runners each represent a different storage device. So starting off with the first runner, they are a mile world champion, so they are used to running a longer distance. And as you can see here, they have a great amount of energy and are able to finish the race, however, at a slower rate than the other racer. And this is because this symbolizes the battery. And this is because the battery has a high energy level and is able to do things over a greater amount of time, however, it has less power. Then at the bottom you see a sprinter who's used to running 100-meter races. As you can see, they start off strong, but they fall flat and don't even finish the race. And this sprinter represents a capacitor. And it has a high power but very, very low energy, so it is unable to finish. And then in the middle we have an 800-meter world champion. So they're used to running this race, and so they have a high power and a higher energy level. However, if they were put in a 1-mile race, they wouldn't be able to finish as fast as the battery. Therefore, it represents a supercapacitor, so it's an in-between of both the battery and the capacitor, so it has higher power and higher energy.
So there are some limits to this analogy. So it captures why supercapacitors are better and how they differ from batteries and from normal capacitors, but they don't show some of the science behind why that works. And so at a nanoscale, as previously discussed, carbon, we used activated carbon, which is a nanoporous material, meaning it has very small holes in it. And this means that the small particle has lots of surface area. And this combination of a high surface area and this ion that is connected to another panel means that there is also a short distance that it has to travel. So this combination between the two means that these supercapacitors create an efficient balance between power and energy, as depicted in this analogy. But the usage of nanomaterials to create fast charging storage devices that we can use over and over allows us to more effectively store and use energy.
Thank you. Thank you.
Questions?
So, if these supercapacitors are so effective and they charge fast and they store a lot of energy, then why aren't we using them everywhere? What are the limitations that stop them from having taken over the world?
They store a good amount of energy, but not for long distances of time. So like they have like buses in like China or Japan, and they run on supercapacitors. However, every time they stop, they charge because they're unable to hold that amount of energy otherwise.
And just to add on to that, an example is in Tesla cars, they do have supercapacitors, but they also have batteries. So an interesting thing about specific to Teslas is they use supercapacitors for high energy bursts. So going from a quick range of speed from like 0 to like 100 miles per hour. They use that for the very quick power jolts, but they also use the batteries to keep the supercapacitors running. So they still use the batteries to kind of support the supercapacitors, and that's still kind of, as a science community, we're working to just make the supercapacitors more effective.
So I'll add on to the question. So I think you mentioned a couple of applications. Can you give a few more, like especially for capacitors?
Well, for us in our experiment today, we actually used it to charge light bulbs, where you saw that something that's battery powered, where in our instance it was actually plugged into the wall. We saw that it was more effective in the battery sense, but in the supercapacitor sense, it could you could charge it way faster than you could with a battery. You turned it on for 30 seconds, and then you could run it for 30 seconds. So it was charging super quickly. And so I don't know if I have a real life application, but that's what we used to do.
That is actually interesting that you mentioned that, because there is one application where you want a flash of light and they actually use capacitors for it pretty frequently.
Mm-hmm.
Can you think of what that would be? If it's a flash of light?
Sirens, a flash of
Strobe
light.
lights.
So what what instance would I want to use a flash of light for something? Like if I wanted to say capture something.
Like a photograph.
For a photograph, right? So actually a lot of cameras, especially like digital cameras, utilize capacitors to recharge and discharge quickly the flash of light, because for those big nice flashes, I mean not probably for your cell phone cameras so much, but for like digital cameras and the ones that they use in the studio, they actually use capacitors for that pretty frequently, because you don't need a ton of energy, but you need energy very quickly. So that makes capacitors a really good case for that. So it's kind of like you guys were saying, there's no like perfect, like supercapacitors don't need to be used for everything, but they're very, very good for some things, just like batteries are good for some things and capacitors are good for some things.
Hi. What kind of effect does heat have on the storage of energy? Like, and the reason I ask is a lot of times people will keep their batteries in a refrigerator, or like on the Tesla car, if the car gets hot, it reduces the range of mileage. What kind of effect does that have, or why is it affected?
I mean, heat on any battery isn't very good, just because the batteries themselves can overheat and just malfunction and possibly blow up. But yeah.
So think about it this way. So
Okay.
what makes capacitors fast? Or what makes batteries slower?
They're slower because they take longer to charge.
And
so-
how are they getting charged?
So we talked about lithium-ion batteries, and so in that sense, the lithium ions are moving around, and in a battery, they're actually separating the layers of the substance they're in, so that's actually a really slow movement, and the lithium has to move through a substance, and that's way slower than it is in something like a capacitor, where it's actually just moving way faster.
Yeah, so batteries go through a chemical reaction, right? Whereas capacitors, you're just doing it on the surface itself.
Mm-hmm.
Right.
So what role might temperature have in a chemical reaction.
It would speed it up versus slowing it down.
Yeah, so if you cool something down, would it speed up the reaction or would it slow down the reaction?
Slow it down.
Exactly. So that's why people put things in freezers, batteries in freezers, because it slows down the chemical reaction. But for capacitors, it's not going to matter at all. For batteries, it will.
Any last questions? And if not, let's thank our speakers.